Good evening, everyone. It's now about 4:35 p.m. Central Time, 5:35 Eastern Time. So my office hour started about 5 minutes ago. I was just waiting to see if anyone joined this evening. And so far, no. So I'll do what I've done in previous weeks and just kind of pick something here related to what's going on this week in the course to kind of go over. First off, this is the Unit 3 module here in Canvas. You can see that we'll be covering modules 5 and 6 on the Cisco Academy. Skip through this here. You want to check these out, but yep, that's it. So modules 5 and 6. Again on the Cisco Academy. So if we take a look at that real quick, you can see here our topics this week. Our primary topics are spanning tree and ether channel, and these are both two layer 2 technologies that assist with redundancy. Okay, so going back to our course in Canvas, as far as the assignment for this week, you have the lab based assignment, and then the exam with the exam in the Cisco Academy on modules 5 through 6. So you want to make sure you knock both of those out this week. Taking a look at the assignment. Not a whole lot going on here. You have Packet Tracer Lab on slide 519, and as it mentions here, all that you need to do, or all that you need to submit rather for this assignment, is the table from part 1, step 2 of the lab. So you can just paste this completed table into your Word document, and that's all that's needed there. Then the last two labs that you have for this week are the Packet Tracer labs on 624 and 634, and so again, that's it. It's just those three labs. So fairly light week as far as the labs go. Going back to the Cisco Academy, you'll see that Chapter 5 has just 4 sections. The first section talks about the purpose of spanning tree, and then the second section gets into the operation of spanning tree, and we'll kind of take a look at that here in just a second, or we'll take a look at something related to that here in just a second. 5.3 talks about the evolution of STP. STP's been around for quite a while, so it's changed a lot over the years. The original implementation of STP is not even used anymore. We're using other technologies like per VLAN spanning tree and rapid spanning tree. Module 5.4 is just kind of a quick review for you. Chapter 6, Ether Channel. Again, just 4 sections in this chapter. The first section is on the operation of Ether Channel. The second section, you'll learn how to configure Ether Channel. And section 6.3, you'll look at verifying and troubleshooting Ether Channel. And then 6.4 is just a review of that. Okay, so I want to take a look at a couple of things here. First, I want to look at, just show you guys here a video, just a short, I'm not going to play all of this video here. Let's see, is that the one I was looking for? Yes. Okay, so we'll take a look at this video. Obviously, this video is 1 hour and 4 minutes. So, if you want to check this out, watch more of it than what we take a look at here. here's the link up here. You can or you can search by the title of the video here. So this video gives a pretty good rundown on spanning tree, and it'd be a good summary of the topic and what all that you're learning about STP for this week. Okay, so I'm going to move that out of the way, and let's go ahead and take a look at this.
How when an IP address has changed, things can change. And so I had OBS Studio set up where it was using a fixed IP address to stream from instead of the default address. And so my computer had been gone for a few days. Got a new IP address for my DHCP server, and it wouldn't stream. All right, so anyways, great to have you. Thank you very much for joining me today for CCNA Sunday. We're going to focus today on a little thing called spanning tree protocol. I happen to really love spanning tree protocol. Let me tell you why. It's one of those things that it's important to understand how it works, but it can also save a person's bacon in a production environment if they're aware of why it behaves the way it does and what it does. So to start off, the word protocol, spanning tree protocol. A protocol is nothing more than a set of rules, of how something should operate. And if devices agree on those sets of rules, they can communicate and work with each other. So spanning tree protocol is simply a set of rules that layer 2 switches agree with and work with and participate in. And I have some basic objectives for our time together, and they are this. Number one, why would we have layer 2 loops in a network? I mean, what exactly is that? Why is it a problem? And so let's start there with the challenge of a layer 2 loop. And to do that, let me share with you, let's do this. Let's go to a computer. And let's go back to this PC right here, to this client PC on this network. And this is in one of my labs. Let me go grab the client PC. All right, so this is the client PC, and if we bring up a command prompt, which I'll do right now, and we type in the command ARP space -A, that's going to show us the current ARP cache. That's the layer 2 addresses that this computer knows about other devices on the same local network. So at the moment, this device knows that to reach 10.16.0.30, and this is off our local interface 10.16.0.10, that if we wanted to forward a frame to 10.16.0.30, that we would encapsulate or use the layer 2 address of this bad boy right here before we sent those bits on the wire. So if you haven't yet seen our session on layer 2 switching and trunking, check that out. We'll talk all about the details of how layer 2 forwarding works. But the challenge here is that if we have redundant paths in our network or parallel paths in our network, there's the opportunity for, let's think we're going to throw something. Let's imagine we're going to throw this. We throw it into the network. If it just kept looping and looping and looping forever at near the speed of light, or however fast the network can forward it, that's going to be a waste of energy if it keeps looping endlessly. So I want to share with you a protocol analyzer right here. And a protocol analyzer is simply a way of looking at network traffic. I've got some captures right here. In fact, you know what? Let's just not look at one. Let's capture one. Let's imagine that we want to ping. Let's go back to our topology for a moment. Let's say we're right here. We're the client PC. And we want to ping 10.16.0.30, PC3 right here. So the traffic is going to have to go over these links. And I have a pen and I know how to use it. Let me get up my, not that. Let me get a pen so I can actually illustrate this and we can be on the same exact page. All right, right here. So these links right here in red represent trunks. And from our previous discussion, the trunk is simply a link between two devices that allows multiple VLANs to go over. So if we have VLAN 10 and 20 and 777 across the trunk links, we're going to add a little 802.1q tag, and so that the receiving switch can know there. So all the links here in red are trunk links. So let's imagine that Bob is sitting at this computer, and Bob types in ping space, and he pings the IP address of 10.16.0.30. Well, if Bob does not yet know the layer 2 address of this PC, he's going to do an ARP request. And that's what I'd like to go ahead and generate right now. I think it'll be fun to do. So we'll go back to our client PC, Bob's PC, and it is right here. And let's do an ARP. That's ARP space -D space asterisk.
And that's going to remove everything from Bob's local ARP cache. So if we do an ARP-A again, he now no longer knows about 10.16.0.30. And before we try to reach that device, let's go ahead and do a capture. So we'll launch Wireshark. It's just a fun protocol analyzer. This is local on Bob's computer. And we'll capture all the traffic going in and out of this interface. And we'll minimize that. And then we'll just do a ping. So we'll do a ping to PC3, which is 10.16.0. I'm just going to check my diagram again. 10.16.0.30. Okay, same logical IP network, same VLAN. And let's go back to our lab. And we'll do 30. Press enter. And this first one took a little bit longer, 161 milliseconds. And that's very likely because they had to do the ARP first. And then the other three here proceeded. Well, that last one took a long time too. But ARP happened. So if we do a up arrow key a few times, ARP-A shows us that we now know the layer 2 address associated with PC3's IP address. And that was courtesy of ARP. So, because we captured that, let's go back to our protocol capture. We'll click on the little stop icon up here to stop the madness. And there's a lot of ARP traffic, but the one we're looking at is from 10.16.0.10. Wow, look at all that traffic. Okay, it's going to be before the pings. That's a good clue. So here we go, right there. Okay. Dang it. Hold on a second. I got a little bit too crazy with the mouse. Okay. Where is the ARP request? 10.16. I'm probably looking at it right here in front of me. What I'm looking for the ARP. Unless it somehow ARPed before. It looks like the response. Maybe I cut some of it off. Okay, I'll tell you what. No problem. We're going to quit without saving. I fumbled figure something. So let's clear the ARP cache. ARP-D. Let's go ahead and verify it's not in the ARP cache. We'll start the capture. Make sure the capture is running first. And then we'll go ahead and we'll capture it. Alright, so now that's capturing. Let's go back to our client PC, minimize this, and do the ping. I'm just using the up and down arrow keys. Alright, so there's our ping. Let's go take a look at the protocol capture. This time I won't fumble finger it. Alright, so here, right there, is our ARP request. So I'm going to highlight that. And if we look at the details of that, that is our PC at 10.16.0.10 with his source layer 2 address, sending out a message at layer 2. He's sending out a broadcast, all else, and saying, hey, anybody on the network, 10.16.0.30, if that's you, if that's your IP address, please respond back and let me know what your layer 2 address is. And then the next packet, we had that response. But what I'd like to focus on is this broadcast right here. A broadcast is, on a VLAN, on Ethernet, it's like shouting. And so we're simply shouting to everybody on that network. And let's take a look at what our topology would do with that if we didn't have something to protect us. And let's take a look at this topology right here. So here's Bob. Bob sent this broadcast into the network, and the switch received it, and the switch is going to forward it over these links. So currently these are trunk links. And so let's imagine that the broadcast gets forwarded this way. So switch 1 sends it, tags it, sends it to switch 2. Switch 2 sees it, says, oh, it's a broadcast for VLAN 10, forwards it to all ports associated with VLAN 10, including the trunk, so it goes down here. Switch 3 receives it, says, oh, that's a broadcast for VLAN 10, forwards it here. Switch 1 says, oh, hey, a broadcast for VLAN 10. I better forward that to all devices that need to see it, plus send over the trunks, and that would just continue looping unless we had something that identified that we had parallel paths. We had redundant paths, which we do here. So what happens without something like spanning tree to stop the parallel redundant paths from all forwarding? We would have packets that broadcast that would loop endlessly like this, clockwise, and also like this, counterclockwise, as they went over these links, and they just keep on going and going and going forever and ever. In fact, if we take a look at, in fact, we can do this right here. If we look at the client PC once again, and we just look at any one of these packets. So this is a ping reply. See at layer 3, for the IP information at layer 3 in the protocol stack, we have this really cool field, which is right here. It's called time to live. And here's how the time to live feels. This is not how it feels. This is how the time to live field works. If you and I are a router and we're getting a packet at layer 3, we're looking at it and saying, oh, I need to forward this, we're going to decrement the time to live every time we forward it. So get a packet, make a routing decision, decrement the time to live, forward it. The benefit of that little field in the layer 3 header is that if that time to live goes down to 0, routers are not going to forward it anymore. They're going to say, well, this packet's time. Let's take a look at layer 2 and see what's at layer 2 that might help prevent a loop, like, for example, time to live. So here's the layer 2 information right here. Source layer 2 address, destination layer 2 address, and you'll notice there's nothing in that layer 2 header that says they're pulling, and they're amazing. A lot of work. A lot of the dogs, everybody's doing a lot of work. Well, there were some vacationers watching, and there's a musher, and the sled dogs had just stopped cold, and the musher went up, got a stick, not a huge stick, but a little stick, and just whacked one of the dogs right in the back of the neck, and the dog, whoa! And then the dog got back in line because the two dogs had been fighting, and then the team started running again. And the onlooker, when they came at the finish line, they were doing photos and things, and the onlooker, the vacationer, said, "What's the secret?" And the musher, the driver, said, "You have to know which one to hit." Now, that's like spanning tree. Spanning tree is going to be sending these little messages across the network, layer 2 messages, and saying, hey, do we have parallel paths? And if we do, bonk! It has to hit links, meaning not tell them not to forward. They call it blocking. And that way those ports, even though they're present, they're connected from one switch to another. If they're redundant and they get chosen to not forward traffic, spanning tree is going to say, hey, I know you're willing to forward traffic, but don't. And that's the concept of spanning tree. Identifying parallel paths and then specifying that we're not going to forward on certain paths. So that's what it does. Spanning tree identifies parallel paths in our network, and then it automatically not disables the ports, but stops the forwarding of traffic on those ports. So if we're looking at this topology right here, here's how we could solve this problem. We could just get rid of this link right here, and get rid of this link right here, and then we wouldn't have redundant paths. We just have the path from switch 1 to 2, and switch 1 to switch 3, and if these links weren't here, these segments between the switches, if they weren't there, there would be no redundant, there would be no parallel paths. We wouldn't need spanning tree. Now, what's the negative side of only having one connection between switch 1 and switch 2, and one connection between switch 3 and switch 1? If you're saying, well, Keith, if we lose a link, if there's a problem in the network, we're going to lose service. And the answer is, that is absolutely straight on. So we want to have the redundancy in place. However, we can't allow all the traffic to forward on all the links because there will be loops at layer 2 unless we use spanning tree. So on commercial switches like Cisco Catalyst switches, spanning tree is enabled by default, and it might be important to understand how the rules are played with spanning tree. And here's the basic rules. So our objectives for this session is to understand why layer 2 loops are a problem. And the answer to that is because there's no time to live function inside the header. One broadcast could go on forever and ever and ever unless we identify that we have parallel paths and train the interfaces to not forward on one or more of those paths. Here's how STP spanning tree protocol operates. It's a collaborative effort. We take a group of switches and they're going to talk to each other. They're going to get chatty. And the way they get chatty is they send back and forth these little itty-bitty messages, and they're called, it's kind of a long term. It's a bridge protocol data unit. Bridge protocol. There's just these teeny little messages about every 2 seconds. Boom, here's the information, here's the information. And these bridge protocol data units are how these switches can identify that there's parallel paths in the network. And so spanning tree, the way it works is it has an election, and they choose one. For every VLAN, there's going to be one root device, one King Kong of spanning tree. Now, they call this device a root bridge. And I thought to myself in the early days, why are they actually, in the early days when I learned it, we were using bridges, and that's why the term comes up. A long time ago, before high-speed switching came up, we had bridges, which act like 2 or more switch ports on our switches today, with layer 2 forwarding and all the rest of the same process. But now we have a separate switch port for every device on the network. So in the old days, when this was written, it was called spanning tree protocol, and we elected one root bridge. So when we think of the word root bridge, think of one switch that's going to act as the root bridge. If you want to call it a root switch, you can. No one's going to laugh at you. But technically, it's called the root bridge. So I've got a question for you. Imagine we have these 3... Wait, let me back up. It's not going to take a lot of imagining. Check this out. if we have these three switches, and we need to choose one of them to be the root, like the starting point for deciding how we're going to forward or not forward, and decide that root bridge. The way they do it is they have something called a bridge ID. And a bridge ID is a number. It's quite a large number, but it's going to be unique for every switch. So switch 1 will have a bridge ID, switch 2 will have a different bridge ID, switch 3 will have a bridge ID. We can take a look at how that's created, and we will in a moment. But when I think of bridge IDs, I think of golf. And you might say, Keith, wait, what do you mean? You think of golf when you think of bridge ID? Yeah, I do. Almost every time. Because in golf, think about it, how does a person win at golf? The last time I swung a club was about 3 years ago in a simulator. So I'm not good at golf at all. But I know the rules. I know who wins is the person with the what in golf? The lowest score. So if we have 3 switches and all of them have a unique bridge ID, the one that's going to win is like golf. It's the lowest one that wins. So what they do is, when they're powered up, they start sending these little love messages, these bridge protocol data units to each other to communicate over those links. Hey, here's my bridge ID. Sort of like this. Let's see if I can actually make sure you can see these. It sounded like a really great idea when I put them together earlier today. Hold on a second. Let me go ahead and bring up this so I can verify. There we go. You got to know when to hold them. Know when to fold them. So basically, each switch has a bridge ID. They know what their bridge ID is, and they're going to use bridge protocol data units, these little BPDUs, send them across the links to the other devices, and basically, everybody gets to read everybody else's card. So switch 1 has one bridge ID, switch 2 has a different bridge ID, and switch 3 has a different bridge ID. Which one's the lowest? I'll let you choose. And I'm looking at the cards in the monitor here. It's this one right here. So the switch that has the lowest bridge ID gets to be the King Kong of spanning tree, meaning they call it the root bridge, the starting point, the core of the tree for spanning tree. That's how it's selected. So a couple things we've learned so far. Number 1, spanning tree is important because it has to identify if we have parallel paths, redundant links in our layer 2 network, which are a good idea in case we have a failure. Then secondly, amongst themselves, based on the lowest bridge ID that they've communicated with each other using BPDUs, they're going to choose one as the root bridge. And he wins. So basically, whoever has the lowest bridge ID is going to be the root for spanning tree for the entire spanning tree for that VLAN, for that network. All right. So that's the first step. Elect a root. Now, what happens next is quite interesting. I think in my mind that everybody wants to be the root. I want to be the root. I want to be the root. Like only one switch is going to be the root switch. So everybody else, meaning all the other layer 2 switches, are going to fall in line. And they're going to say, okay, we agree. I mean, we can see, right? Your bridge ID is lower than mine. We learned them via BPDUs that were being sent. We agree. We're over it. And then they have to determine, okay, in this topology, which of my many ports, says the switch, which of my many ports is the most cost effective to get to the root switch? So let's go ahead and annotate this on the screen. So let's imagine that, and let me pick on this guy right here. Let's imagine that this switch right here became the root. Now this is also happening for all of our VLANs. And so for this discussion, let's play with VLAN 10, although the output is going to be very similar to VLAN 1 or VLAN 10 or VLAN 20 or VLAN 777 until we start tweaking things. But let's imagine we're taking a look at just the spanning tree for VLAN 10, and switch 3 is the root bridge. And, oh, I just had it a moment ago, but remind me. Out of these 3 switches, how did they determine who's going to be the root? How did they know who's going to be the root bridge? So if somebody would just chat that in, or everybody chat that into the message board, just to confirm that we have that the switch that has the lowest, it's like golf, I remember that, the lowest bridge ID becomes the root. And once he's the root, everybody else agrees, they've seen the BPDUs, they condescend, they say, great, I understand, and you're the root. So the second step for those bridge for those switches, and let's go ahead and let's call these guys loser 1 and loser 2. Now if these were people, that'd be so rude, but because they're switches, we'll be okay. So what does that mean they're a loser? That just means they're not the root bridge. So we're gonna have one root bridge and then everybody else who is not the root bridge. In fact, let me undo this. So the next step for these switches is to say, okay, great. What's the best way, or what's the most cost-effective way for me to get to the root? So switch 1 knows that switch 3 is the root, and it's going to go ahead and identify what's called a root port. Now here's the secret for a root port. A root port is on the losers. So on the loser switches, the switches that didn't become the root bridge themselves, each of them are going to have one and only one root port, and that's the best path that they're going to use to forward in the direction of the root. That's it. Now, the question is, how do they decide that? Well, here's how they decide it. More cards. To choose the root port, each switch is going to say, okay, I've got these BPUs coming in on multiple interfaces, right? I know where the root is, and it's going to say, what is the least cost for me, maybe this is switch 1, to get to the root? And it looks at its cards. It says, okay, the cost on one port is 4, the cost on another port is 2, the cost on another port is 6, and again, it's a lot like golf. So each switch, as it determines which port is going to be the one that I'm going to forward towards the root, it's going to go ahead and pick the one that has the lowest cost, and that port is going to be identified as what's called a root port. It's a port that's forwarding in the direction of the root switch. So it would look like this. And for this diagram, just I'm going to give you a heads up right now. These are all gigabit links, and the cost of gigabit links in spanning tree is 4. A cost of 4. So what would happen is switch 3, these BPDUs would be flowing out from switch 3, and switch 1 would receive those. And in those BPDUs, there'd be an advertisement that the cost is 0 because this is the root switch. And switch 1 would see on this interface, gig 2/0, its cost is 4. So it adds up the cost on that interface plus the advertised cost from the root, and the total would be 4. So out this port, it would be a cost of 4, and for these other ports, it'd be a lot more. And let's talk about that. So switch 3 is the root, advertising at a cost of 0. Switch 2 receives that, cost of 4. So now when switch 2 is advertising BPDUs down this way, it's also saying that the total cost from switch 2's perspective is a cost of 4, and switch 1 has a cost in this local interface of 4. So effectively, it'd be a cost of 8 on either of these links. So when switch 1 is identifying, okay, which port is the best one and only one I should use to forward towards the root, it's going to go for, like golf, the lowest cost, and that port in this topology, if this was the root, is going to be the root port. So switch 1 would show 2/0 as being a root port. That's it. I mean, that's how switch 1 would do it. And switch 2 would do the same thing. Switch 2 would say, okay, great, what's the cost to get to switch 3, who's the root? And in this topology, this would be a cost of 4, advertised cost of 0, plus the cost of 4 on the local interface. So this would be the root port, and it would make its forwarding decisions, and this would be a forwarding port in the direction of the root. So here's the key. For the losers, I'm going to put that up here again. For the loser switches, they are going to have one root port, which is the port that is their best option if they choose to forward traffic in the direction or towards the root bridge. So each switch gets one root port apiece as a forwarding option. So also, this is also called a role. So if you ever see the concept of a root port, realize that's the role of that port, and root ports are also in a status of forwarding. So a lot of times what happens with spanning tree is there's a few terms involved. And so when people start talking about forwarding port, root port, I just want to clear up that the actual role of this port is called a RP, a root port, and root ports by default are always forwarding in the direction of the root bridge. So a root port So to summarize, root ports are always forwarding in the direction of the root bridge. That's it. All right. So let's talk about, let's talk about one other direction. In fact, I'd like to ask you, and then we'll talk about it together. If we have two options about forwarding traffic, and if we're not the root switch, or even if we are, we have two options regarding forwarding. One is towards the root bridge, and that's what we just described. So if we have ports that are forwarding, and we have one each per switch that's forwarding towards the root bridge, that's referred to as the role of a root port. There's also an option to forward away. What do you mean away? Well, if we have a port on a switch that's forwarding away from the root switch, it would look like this. Let me put a different color on here. Let me go ahead and use blue. That'll work. Oh, changed my mind. Let me use whatever color that is. All right. So if we have a switch 2, for example, it's forwarding, and it's forwarding on this port or this port. In fact, let me go to blocks. It's easier to see. If it's forwarding here, that would be an example of forwarding in an opposite direction or away from the root. So the root port would be forwarding towards the root, and the ports that are forwarding away from the root in the opposite direction would be considered forwarding away. Those also have a role, and that role is called a designated port. And it's always forwarding, by the way. So if you have a designated port, it means two things. It means it's forwarding away from the root switch, and it's also forwarding. Two things in the same sentence, actually. All right, so for us, let's take a breath. A couple basic things. Number one, if we have loops at layer 2 that don't go unchecked, we're going to have broadcast storms that just loop and loop and loop and loop forever at layer 2, which is a problem. So spanning tree steps in, and it's on by default on commercial switches, including catalyst switches. And spanning tree says, great, we're going to go ahead, if it's running, if the service is running, the spanning tree protocol, it's going to elect a root bridge. And it does that based on the lowest bridge ID. So whatever switch, by advertising the BPDUs across the network, if whoever has the lowest bridge ID becomes the root. Then the other switches who are not the root identify their root ports, the best path to get to the root. And then any ports that are forwarding away from the root, those are referred to as designated ports. So far, we haven't talked about any type of blocking whatsoever. We've talked about identifying a root switch, we've identified root ports, and also designated ports. But we do need to bring in blocking into play, so let's go ahead and do that right now. And let me clean up the screen just a little bit. There we go. All right, so let's go ahead and imagine, let's take it from the top. Let's say Bob is right here. And Bob is going to ping this device. He sends an ARP request as part of that ping, and we don't want to have a layer 2 loop forever and ever here. So spanning tree beforehand figured out the topology. Switch 3 becomes the root bridge if it has the lowest bridge ID. And we have two roles we've talked about so far. We have ports that are designated. And designated means this. We're forwarding traffic, forwarding frames away, or in the opposite direction of the root bridge. All right. And then, so on this switch, the root switch, because it is the root, it has the opportunity of having all designated ports. If this had 20 ports, they would all be designated. Because let's think about the definition. It's forwarding away from the root. It is the root, so everything leaving it is forwarding away from the root.
And one thing I'll add here, guys, is that's true for VLAN 10 because again, that's what that's all he's looking at. But potentially, if we're using per VLAN spanning tree, it could be different for a different VLAN. So just keep that in mind.
So all of its ports would be designated. And then regarding root ports on all the other switches, that is in a state of forwarding towards the root. So in this case, switch 1 would calculate that this is the best path based on the BPDs that are being shared. So this would be the root port. And then switch 2 would identify that this is the best path. It would be shown as the root port. And then the tricky part comes in up here. Now, on these segments right here, if somebody's got to, let's talk about the reality here. Somebody's got to block traffic. Otherwise, we're going to have a loop. And so every switch is going to have one root port, and every segment, which is, let's say, it's like every connection between two switches, is going to have one designated port. Somebody who's forwarding for that segment. And that means if you've got these two switches, switch 1, switch 2, and they both are connected, on one side, we're going to have some designated ports that are forwarding away from the switch. And on the other side, we have to have some blocking going on. So let's take a close look at how that happens. So we talked about the route election, which is based on cost. Excuse me. I'm ahead of myself. The route bridge, which is based on low bridge ID. Right? And then for the other devices, they then calculate their route ports. This would be A, elect the route. And then on the non-route switches, they identify their route ports. And then for C, then we need to go ahead and calculate the designated ports for everything else. DEZIGNATED ports. So these are going towards the route, these are going away from the route. So on the route switch itself, all ports are designated, meaning they're all forwarding, and they're all forwarding away from this device, the route bridge. So then here on switch 1 and switch 2, the question comes in, okay, who gets to be designated? Is it going to be switch 1 or is it going to be switch 2? And to ferret that out, the one that gets to be designated is going to be the one with the best cost. So what happens is there's going to be BPDUs that go between switch 1 and switch 2. And in those BPDUs, switch 1's going to say, hey, my cost to get to the route is 4. Beat that. And switch 2 is going to say, my cost to get to the route switch, is 4. Beat that. And you might see that we have a tiebreak. We have a problem here because both switches have the same cost. So what do you do next? Well, if the cost is the same in this scenario, the next tiebreaker is the lower bridge ID of the two. So neither one of them won the spanning tree route bridge election, but between them, switch 1 and switch 2, the one that has the lowest bridge ID in this scenario is the next thing to look at as a tiebreaker. So let's imagine that this guy has the lowest bridge ID, and let's imagine that this guy is in second place with the second best BID. I'll put bridge ID there, and this guy is the third as far as the third best bridge ID. What happens is, as far as who gets to be designated for these two segments, if the cost is equal to get to the route, this switch number 2 is going to say, oh, I win because I have a lower bridge ID than you do, all other things being equal. And that would make this port designated, this port designated, and then what would happen is you're only going to have one designated port per segment. And as a result, switch 1's going to say, oh crap, that means I lost. And it's true. So these two ports would go into what's called blocking state. BLK for blocking, because that's parallel paths, redundant paths. So neither of these two interfaces from switch 1's perspective would be used for forwarding traffic. And our spanning tree topology would effectively be the link between switch 1 and switch 3, between switch 3 and switch 2, and then the two links from switch 2 over to switch 1, they would be forwarding, but switch 1 would never forward in this direction. It would never forward out 1/2 and 0, 0, because it lost the spanning tree process.
Okay, so that pretty much wraps up what I wanted to cover for you guys here as far as the spanning tree process and how everything works. I guess a couple of things. One, you'll find I like to use YouTube a lot because there's a lot out there. I'm very much a believer of not recreating the wheel, so to speak. And then too, I like to find when I can, I like to find presenters that are a little more entertaining, like this guy here, and it tends to keep your attention a little better. I don't have near the I guess screen presence, you could say. So I'm sure you, whether you realize it or not, you enjoy listening to him for 40 minutes much more than you would enjoy listening to me for 40 minutes. But anyway, again, that's all I wanted to cover here. So we see we still have no one who has joined for the office hour, so that's fine. No questions to address or anything. We'll just stop it here.